Hello everyone, my name is Dharamveer Kumar. I'm a PhD candidate at IIT Bombay, and today I'll be solving assignment 2 so that it will help you understand what the solutions are, and then probably will help you in assignment 3. If you have any questions, there are groups on NPTEL or the comment section on my YouTube channel. You can also pose your questions over there. Okay, so I'll just do assignment 2 today as much as possible in the given time, and we'll see how it goes. Okay, so yeah. Just 1 second. Sorry. Okay. I think today no one was able to join as of now. I was waiting, but I think I'll get started now. I waited a lot. Yeah. So, assignment 2. Okay. Here's question 1, which talks about what does it mean for something to be bounded. Okay, what is this? So if there is a, so we are talking about only in real number systems, right? So finally someone has joined. Okay, so there was a question about boundedness of empty set. Is it bounded from below or above, or it is not bounded, and what does it mean? So I've not started anything. I'm just talking about what does it mean when we say that empty set is bounded or not. Okay, so how do we define boundedness? Okay, so let's say there is a subset A of R. Okay, we call it bounded from above if there exists M in R such that so this is a tricky statement, more of it, you can take it as axiomatic, that if A is empty, any property it will satisfy, right? Because if anything is true for all x in A, there is no x, then it is true. Similarly, we say that phi is open and closed, because for openness there is a property that it should satisfy for every x in A. But if there is no x in A, that means it is satisfying that. So hence, and for lower bound, if there exists small n in R such that, so empty set is bounded from above and below. Now this is a very good example. This is bounded from above and below. What are its upper bound? All real numbers. So if all real numbers are its upper bound and lower bound, what is supremum? What is the lowest upper bound? So think about it. Can you answer? What is the lowest upper bound for an empty set? But is minus infinity a real number? So what do we do in lowest upper bound? What do we do is we add plus infinity and minus infinity. That is a acceptable range. So that's why it's minus infinity. Good. Again, this is a very pathological set. These are like corner cases, not the usual case. Okay, so usually this will not be a case, but yeah. So another question is, these are important things, but not as of now, not for if you have to solve some problem. Yeah. So let us state true and false. So let A be 0 and 1, B be 2 to 3 included. Then every beta in 1 or 2 is a supremum of A and infimum of B. What do you think? True or false? So whenever there is like infimum and supremum, they are always unique. So this is false. But this is a bound. So basically where is the solution? This is set A, right? 0 to 1, this is 1 to 2, 2 to 3. This is included. So all number in 1 to 2 is an upper bound on this set. So this is what it means. This whole thing is an upper bound. There is a bigger upper bound and so on. So upper bound, there is no limit. That's why we need supremum. Lowest upper bound, because biggest upper bound could be anything. If there is one upper bound, you can just take it to infinity. So there is no point of there is no maximum upper bound, but there is a lower upper bound in this case, which is what? In phi it was not there, but in usually there are fixed unique number which are lowest. Okay. Similarly for 2 and 3, it is a lower bound. So what is the infimum of 0 to 1? It is 1. And for B, what is the supremum of 0 to 1? So for A, supremum of A is 1, infimum of A is 0, supremum of B is 3, and infimum of B is 2. Okay, and in this case, since 0 and 1 or 2 and 3, they are lying in the set itself. They are in the set. That means this is also a maximum. This is also a minimum. Maximum, minimum. In case you don't remember, I told you, if it was 0 to 1, 1 is not maximum. So, but you want to understand maximum and minimum concept, right? But there is no maximum over here. That's why this concept of supremum arose. Okay? So still you can talk about, there is something, right? One, it's something in here. So you want to understand that. One is totally different from the other points. So you want to give it a special name.
This particular point, can you explain once again?
Oh, okay. So if I'm talking about this set 0 to 1, okay, 0 and 1 are not included, right? So do you understand that 1 is the supremum?
Yes.
Yeah. So but 1 does not lie. So this is, let's say, A. Does 1 belong to A?
No.
No. So whenever supremum belongs to the set, that supremum is nothing but a maximum.
So wherever maximum is not there, there we will call it a supremum.
Yeah, wherever maximum does not exist, we call it a supremum. That's it. Because
Okay. Okay.
think about 0 to 1. 1 is special than, let's say, 1 minus 0.000000001 or anything, right? Less than 1. 1 is definitely greater than all these numbers. So we want to call it a special name for this. It's not included, it's not in the set, but it's still something that is giving us a meaningful information about the set. So that's the point.
So in this question, since A, the supremum of A is 1, that
Yeah.
is not there in beta, so it is false. Isn't it?
No. Supremum is only 1 point. Supremum is exactly 1 point. It's unique.
Yeah, but in this question,
So in
now
this question,
A
they
is
say that every
is
point, every beta is supremum. But it cannot be, right?
okay.
Supremum is only unique. The supremum is nothing but 1.
Okay.
Yeah.
They would have given beta is 1, then that is correct. Right?
No, only for beta equal to 1. But they are saying
Yeah,
that
that is not.
every point is a supremum. That is not true.
Okay.
Yeah. Even if it was like 1 to 2, not every point is a supremum.
Okay, clear.
Only one is supremum, others are not. Okay? So only one is supremum, others are not. Yeah. So now true false again. If A is a subset of R, is closed if and only if A is finite. So for this type of questions, all you need to give is a counter example. Right? See, this is tricky, a bit tricky in real number. All I'm saying is this minus infinity to 2 is open, right? That implies the complement 2 to infinity is closed. And it's not finite. Other thing is, even if we take 2 to 3, this is also not finite. Finite means what? I'm not sure which finite they're talking about, but there are two types of finite. One is has a finite width, the length is finite, or as you call bounded. So no, so closed does not imply bounded. Closed does not imply finite. Finite is something like this: 2, 5, 7, 9, blah blah blah. So this is a set which is closed. It's not finite. Simple examples. These are very simple questions. Just 1 second. Okay, these are very simple questions about. If you don't understand, let me know. Okay. Now again, there is a true and false question. One second, yeah. Let me check if I'm recording or not. Yeah, it is recording. So there exist two intervals. So I hope you understand the difference between set and an interval. Interval is of the form AB, where B can be infinity, or a can be infinity, like from real to infinity, but it has, this is an interval. A set could be union of intervals, stuff like that, and a number itself, something like that. Okay, set and a interval are different. There exist two intervals ij in R such that ij are both non-empty, closed, and ij is equal to phi intersection and I union j equal to R. Visualize it. There are two intervals, okay, and they don't intersect, and their union is R, and they're intervals. Okay, so example of two intervals would be something like this. So on a real line, without loss in generality, if the one at one place, some place will be a starting point, right? Unless it's infinity. And as soon as you have over here, like the first point, the second point has to be but as soon as you get second point somewhere on this side, the right bracket, what happens now? The second interval will be on this side, so it will not cover R. So basically, in this case, all you have is just erase this. So all you have is, without loss in generality, ij is like this and j is like this for non-empty. It's very important that they are non-empty. One could be R, one could be phi if they were empty. So they are non-empty. This is the case. But why is it false? They cannot both be closed because their complement, as you see, I union j is R. So basically, j is I complement. So if j is closed, that implies I is open. So they both cannot be closed. You understand? I equal to j is R. J was complement of I, right? So if j is closed or I is closed, the complement is going to be open. And you saw the example. And it's very important that they are non-empty. If the case was that if this was not given, I could take 1 to be empty, j to be R, both are closed, everything is satisfied. Because phi and R are both open and closed. That's the reason. So it only works when it is non-empty. Okay? I hope you're learning something from here.
No, here
Yeah.
question given is it is I, J both are closed, right?
Yes, they are not closed. That's why it's false. They cannot be closed. If this is the case, they cannot be closed.
Okay.
Because when this is the case, they are complement of each other. This implies that I is equal to j complement. So if one is closed, the other has to be open. But if they are non-empty, only if it was the empty, like you always, whenever you have these kind of things, right, and empty and non-empty is not given, always consider two cases. one where empty and one where something is not empty. Over here it's given it's non-empty, but let's say if it was empty, I is 5, j is r, all the conditions would have been satisfied. Why this is false? Because of non-emptiness. Okay? So whenever you have this type of questions, right, always try to remove one thing and see what are the solutions. Okay? It's very nice. What is the importance of these each and every point? Right? So non-emptiness is, if you remove non-emptiness, this statement would be true. If you remove close, this statement is obviously true. If you remove I intersection j is equal to 5, then also it is true. If you remove I union j is equal to r, just remove any one of them, again it is true. So all of them combined is important for this statement to be false. So you have to think like that. You have to start thinking like that. Not just the question this is given and you're solving it, but okay, what if I remove, what if I change a question a bit? What am I going to learn? Okay, this is a true false question. In assignment of the questions were not mainly of analysis, they are just, how do I say, general questions in mathematics. Simple questions about sets basically. Anyone, any idea how to do this?
It's false, right?
What?
False, right?
This is true.
But prime, it is given prime, right?
Yeah.
Okay, yeah, right. Okay, true. Sorry. Yeah.
Why is that?
Okay.
How do you prove something like this? You remember you must have done in school about how do you do root 2 is irrational. It's literally the same logic. So you start with, okay? So you consider, this is how you learn contradiction. Whenever something like this is given, consider, yeah, or rather I would write assume root p. Oh, I have written rho. Yeah, I'm working on this problem. That's why rho is rational. Okay, what does this mean? That implies, what does it imply? That root p is Rs where Rs belong to Z plus, and whatever the factors and S not equal to, rather, so it is square root, right? So it is positive. So Rs must be positive. Okay, R is not equal to 0, so this means positive integer. Okay, this is how you write it. Totally fine, right? Now what you do is take the LCF, like, so you know this prime factorization thing that every numbers can be written in terms of primes. So whatever you do, you remove all the common factors. Okay, so RSR doesn't have any Remember in school you used to do LCF? Just do that. It's HCF or something like that. Yeah. HCF we call it, highest common factor, and we just divide it. Okay. So now what you do is, yeah. So now you square it. This implies, sorry, this implies r is equal to ps square. So this is what? R into R, this is P into S into S. Right? This is an integer. That implies that P divides R. Do you understand why this is true? So this is R is an integer into R over P is equal to an integer. So over this side there is an integer, over here there is an integer. Is it making sense? So basically what we can write is R is some P times T. That implies this is also equal to P square S, sorry, PS square. This implies R square is equal to P square, yeah, and yeah, so this implies that S square is equal to PT square. From here you cancel P and P, so S square is PT square. This implies that P divides S square, then it divides S. So hence P divides R and P divides S. So I'm not sure if you remember this, so you should know what it is called. It's called prime factorization. So in it's the technical term right now is, so if you want to do is integer factorization. So let's say if you have a term given, let's say integer, okay, so over here R and S are integer, right? So whenever R and S are integer, they are basically in this form. Up to where? Up to any integer, up to all the primes still are over here. Why? Because like if R is a prime itself, it is just a prime into 1. So everything is over here. This is how you write it. What we are saying is In R and S, you remove all the common factors. Okay, more in many cases like n1 could be 0, so n1 to nm are greater than equal to 0, something, an integer. They are also positive integers, basically. Greater than equal to 0 and positive integers. So they could be 0, 1, 2, 3, 4, like something like this. What we are saying is, so this is again a number theory question, not a real analysis, but yeah, for the introduction of irrational we use this. So this is the fact about integers. Okay, how do you get it? Right now, don't worry about it. This is something that is there. Okay, now what you do is remove all the common factors. So there is no prime in both of them which divides them. Okay, now in that case, whenever there is like r, okay, and with prime numbers, so whenever you do r square, what you are doing is and p was a prime, right? So it will be one of the primes over here. Because if p divides r square, so r square is something bigger. So for sure, s is an integer. Okay, so r square over p is definitely greater than equal to 1. So that implies r square something like this. So whenever r square is there, you square with the prime. What does it mean? There must be, so since r square is greater than p, this prime is also here. Just imagine r square is a number in itself, and I've told you all the primes till r. So all the primes till r square. So p comes in that. Okay. So basically p will definitely be one of the primes over here. So if p is one of the primes over here and you have squared it, so some place over here is p to the power 2 n star. So what does it mean? For it to divide, it has to be an integer. You cannot, the primes cannot divide other things. It can only divide this. Okay, so when it can only divide this, what does it mean? That 2n star is definitely greater than or equal to 1. Now n star over here, so if you are doing a square and n star is greater than 1 by 2 or positive, right? This also implies that n star, because these have to be integers and it is greater than half, it's not 0. So n star is at least 1. So this is basically p square. So that's why p is getting cancelled. So if r square is divided by p, that implies r is divided by p. By divided we mean when you divide it you get an integer. This is also a fact about numbers. It also comes from number theory. If r square is divisible by a prime number, then r is also divisible by prime. So that's what we are doing over here. If you think about it, r square is divisible by p because you're getting an integer and s square is an integer. That implies that p divides r. What are you doing now? So if p divides r, then r is equal to some p times t. T is an integer. T is an integer. Okay, what does this mean? That r square is equal to p square t square, and then r square was also ps square. So from here cancel p, because p is not 0, p is a prime. You cancel p, you get s square is equal to pt square. From here again you get that p divides s square, because t is an integer. If p divides s square, then p divides s by this lemma. That means p divides both r and p. So you cannot, but initially what we said, that in r and s, all the primes that are common, like over here if it was like 2 square, 3 square, 5 cube, something like that, and over here it was 2, 3 cube, 5, let's say. Okay, 5 may not be there, yeah, 7, something like this. So you're dividing this 3, you're dividing the 3 square, so over there is 3, something like that. This is how you do it. You're cutting everything off, so there is no common prime. It's not like the prime, all the primes are gone that was there, like over 2 is here, 2 won't be here, 3 is here, 3 won't be here. So this is how you do an HCF. And this is what, from here we get that p divides r and p divides s. So hence contradiction. This is how you do contradiction. It was a little unusual way, but yeah. So this is how you prove, like even for root 2, this is how you can prove. Okay? I hope this is clear to everyone. If not, you can ask me any question. No questions are stupid, okay? Just give me a second. Let's take a second, understand that what I'm talking about. Okay, so I think there are no questions. I'll just save a recording once. Okay. So I hope everything is clear to you. You're able to understand this. My goal is to just make you understand all the silly problems. Okay, the solution is already shared with you, I guess, but I want to like emphasize on deep stuff a bit. Okay, so consider the following set. Z plus means integer greater than or equal to 1. So whenever you encounter something like this, this means all the points, and this means the condition imposed on it. Okay. So what is which statement is true? So there are a bunch of statements. So the options are: A is bounded below but not B, B is bounded below but not A and B are bounded below, A and B are not bounded below. Well, best way to write is neither A nor B is bounded below. Okay, so let's, rather than just solving about boundedness, let's see what this sets are. So for every integer n in z plus, this is a set. Okay, so it's a finite set. For each integer there is a point, and you just find that point. Okay, but this is minus 1 to the power n. Okay, so what does this do? N is an integer, so when n is odd, like 1, 3, this is minus 1. When n is even, like 2, stuff like that, it's 1. Okay, so what does xn, so like let's say A is a set of xn. What are these? Basically you can say something like this, z plus, right? And these xn's are nothing but so when n is odd, they are minus 1 over n. This is minus 1, so 1 minus 1, 0, they are nothing else. And what about when n is odd? They are minus 1 plus 2n square. Okay, what is x1? Minus 1. What is x3? First we are doing odd. Minus 3. What is x5? So on number line, if you want to see, minus 1, 0, over here it's minus 1, so this is basically x1. x3 is somewhere over here, x5, and so on. These numbers lie between 0 and 1. They are always negative, and they are always greater than or equal to minus 1 for odd. What about even? What is x2? What is x4? How do you plot it on number line? So can you see, for an integer, this is a positive number, this is a negative number. Is this number always positive? Right? Can you say this? Basically how you are saying this is because n starts from 2. This is always positive. So over here, so x1 will be somewhere here. This will be always positive, right? And it will actually increase. So this number is positive. So automatically, what is the bound? 0, right? For this even, and odd always lies over here. So what is the total bound of all the set? So that means A is bounded by minus 1, and minus 1 lies in the set itself. That implies A is infimum and minimum. Sorry, minus 1 is infimum and minimum of A. Actually the set are not the numbers are the infimum and minimum. So it's also because x1 is minus 1. So these even numbers are all positive, These odd numbers are all negative but lies in minus 1 to 0. So A is definitely bounded from below. So this goes out, this goes out. What about B? X in R, x square less than 9. Simple way is to plot. If you want to plot x square, always plot. And the value over here is 9. You plot it, you get, cannot be, so this is the bound, this is the set of all x's where x square is less than 9. Is this set bounded? From both above and below. Right, its function both are increasing. So over here it is 3, it is minus 3. Does x equal to 3 satisfies this? So basically 3 is supremum, minus 3 is infimum, not maximum, not minimum. Graph is the best way to see this kind of problems. Okay, that means this is true.
Now this B is both bounded above and below. Is it right? For this
Yes.
condition.
Yeah, P is bounded above and below, not A.
Whereas
A,
but
A-
A is one bounded below, right? Above
yes.
is
Above it will go to infinity
infinity. Okay.
for the, because of the even sequence. Okay. If you want to prove this in terms of algebra, you can do something like this. I think this was given in the solution. Mod x is equal, so all the set points mod x greater than equal to 4 implies right, and 16 is definitely greater than 9. So these points basically mod x greater than equal to 4, if you have minus 4, these set are not all the real numbers. Basically this is the real numbers are so let's say if I call this C belongs to this B ka complement, because this set does not satisfy that condition. This, yeah. Okay, so C is B complement. So from here we can say that there is some complement, this lies in this complement, so this belongs to, this is inside. So B is inside. If you take complements, this change. So B basically, so this is C, let's say. If you take a complement of C, right? C complement is definitely better than B. Whenever you take complement, you change this side. It's like a negative side in what C complement is this, and it is definitely bigger than B, right? B was just minus 3 to 3. So in this way, and if C and C complement is bounded, because whenever you take mod x, this complement is bounded. This is one way to show, but like the best way is always graph. Don't think about anything else. Yeah. Question 7. It's a true and false question. Let S and T be in R, T in R be non-empty subsets. So they are non-empty such that S union T is R. And there is some S and T for all S in S and T in T. Okay, then there exists a unique. This is sign for unique. This was there exists unique beta in R such that S in S for all S less than beta and T in T for all T. First of all, so there are two non-empty subsets, okay, such that their union is R. Okay, how can you draw this? They are not interval. Notice that they are subsets. You cannot do something like this. No, they are subsets. And when they are non-empty, you cannot say that S is T complement. No, big no. You cannot say that.
This can we take minus infinity, less than minus 1 as S, and 1 and above can be taken as T, right?
What?
Now S should be less than T, right? Condition.
Yeah, S should be less than T, yeah.
So can we take like minus infinity to 1 as S and T to infinity as, to 1 to infinity as T? Then that union will be R, right?
Yeah, so basically, now can you see, can there be an intersection? Like just from this, we cannot say this, but using this, there is no equal to. So they cannot be equal. So this implies S greater than T for all S in S and T in T implies that S intersection T is phi. Okay, so now let's say S be any set, okay? You cannot think like intervals because whenever there are very weird sets as well, okay, so you have to be a little critical about when you're talking about like just minus infinity to S or something like that, okay? So like if there is a real line, for simplification you draw 0 and pick one point in S without loss in generality. Since why you can pick one point? Because it's a non-empty set. So let this X be in S. It's non-empty set. It has to lie somewhere. You put it over here. Okay, now T is always over here, so that implies that T is a subset of, and they cannot be equal, X to infinity. Now since S union T is R, that implies that minus infinity to X lies in S. So you're seeing the inequalities over here. Now what they are saying, that there exists a unique beta in R such that the beta is bounded by S. The beta bounds S. Okay, S is over here. Okay. Let there be a beta which bounds S. Okay. Let beta bound S. So S is definitely including minus infinity to x, and t is somewhere over here. And they are phi. Okay, so once it is there, now pick some other point. Either there is a point, so now you make two cases. Either minus infinity to x is S, this is one case, or is an improper set. So there is another point. In this case, there exists a y greater than x in real number such that y is in S. There is another point, let's say y. So as soon as there is a point y, that would imply that minus infinity to y is a subset of S. And you keep doing that unless you hit this. So there will be a point called Z such that it will be equal to S. So S has to be an interval. Because T was non-empty. If T was an empty set, S could be minus infinity to infinity. No one is stopping us. And when this happens, that implies that T is Z to infinity because they don't connect. Okay? So this can be only case. So whenever, right now we are not going to beta, this is the only case when something like this can happen. So basically, given all the conditions, this is an interval. You have to prove that. You cannot just state it like okay, or by intuition. Intuition is good to start, but then you have to prove it mathematically. So now we are saying that there exists a point Z. So basically there exists a point Z such that this is S included in this and this is T. Now they are saying, does there exist a beta or unique beta such that beta is greater than S and T is bounded from below by beta. Take any, let's say take Z. Okay, Z, the number has to be greater than Z for sure, right? But anything greater than Z will not be bounded by T. So false. Okay. Another way to do it like you can do it is since T is non-empty, there exists a T1 in T, right? And the T1 is bounded by S for all S in S. That implies S is bounded from above by a real number. That implies supremum of S exists. Similarly, infimum of t exists. You can do the same thing, same argument. Okay. Now, since t was an upper bound, this implies that supremum of s right. Now, if supremum of s not equal to infimum of t. Okay, sometimes they ask for algebraic question. So from here you understand this, right? What is the supremum over here? What you're getting is equality. So when they are equal, that's okay. But when they are not equal, right? So then you start with two cases. So either supremum of s is equal to infimum of t. Okay. So first case is supremum of s. So from here you divide it into cases. And you want to do this algebra because in real line there are a lot of intuitions. In R2, R3 there are very less intuitions, or in higher dimension space. So you want to do this as well to think how it goes. Okay. So when this is clear, right? So there exists one point in t. So that's why s is bounded from above. So that's why supremum of s exists, and similarly infimum of t exists. And when this is the case, case 1 is supremum of s is equal to infimum of t, and we can call this beta. What was the question? That s should be not equal to beta. So that means, and similarly infimum of t, but supremum of s and infimum of t aren't supposed to be maximum and minimum. So this beta does not belong to s or t, but s union t is what? R. So there is no beta in R. So again, false because of this. Case 2. Whenever supremum of s is equal to infimum of t, and we are calling it beta, right? Because beta is just 1 second. Yeah? So this is the case. So whenever supremum of s is equal to infimum of t. So now from here you have to think a little more. Just 1 second. Yeah. So let's say this is equal, right? Then let's call this so let's say beta is greater than this. That implies, so if beta is greater than infimum of t, right, that implies beta anything just a bit, even a little bit greater than infimum of t, that means this won't be true, not true. This cannot be beta. What if beta is something like this? This implies, greater. You divide into cases. Supremum of s and beta is greater. As soon as beta is greater, that implies that beta is greater than supremum, right? So beta is not greater than s for all s in s. This is also not true. So this is wrong when they are equal. That means beta equal to supremum of s is equal to infimum of t. Okay? But beta is supposed to be greater than s for all s in s. That implies supremum of s does not belong to s. Similarly, infimum of t does not belong to t. That implies they are both equal. That implies beta does not belong to s union t, but s union t was r. So hence false. In this case, whenever if s and t are such that their infimum and supremum are same, this was the case, right? This is the only case that is possible, and I will show that why this case is not possible using algebra. This is not possible only. Why? From intuition and graph I have already shown you. I'll show you from algebra as well. So like, let's say this is the truth, right? Let's call gamma as infimum of t minus supremum of s. Oh, so what am I doing? Infimum of t, yeah. So where does gamma by 2 lie? Gamma is like this. So basically, supremum of s, gamma, infimum of t. This is the relation. Right? But, and gamma is greater than s, right? For all s in s. Gamma is less than t for all t in t. But even if supremum of s is included, gamma does not belong to s union t, and s union t was r. Hence, gamma does not exist. This case is only not possible. And whenever in this case we showed that all the conditions are voided. Okay? Well, this was a little long, but you need to understand supremum, infimum like with a very good detailing, right? Now, so you have in is minus n to n, and jn is minus 1 plus 1 over 2n plus 1, 1 minus 1 over 2n plus 1 for all n in z plus. And let I is equal to union of n in z plus in, and j is equal to union in option A, I is closed but j is not. B, J is closed, but I is not. I and J are both closed. Neither I nor J is closed. Let's see what INs are, right? So what is I1? To start with, I1 is minus 1, 1. I2 is minus 2, 2. Right? I3 is minus 3, 3. So can you see the pattern? Like, what is I2 union I1? It's just I2. Okay, what is I3 union I2 union I1? It's just I3. Okay, and so on. What is I? Is I equal to real numbers? It's always increasing. Is I equal to real number?
I is minus n comma m.
No, but it's going to infinity, right?
Okay. Then it will be real.
But you have to prove it. How did I tell you to prove? So you start with, you have to show both the things. So pick a point x in I. So I is a union, right? That implies x belongs to in for some n in z plus, it belongs to somewhere, right? So that means x belongs to, for some n, like some k, is a better notation. That implies x is real. Now what about real to I? Pick a x in R. I have shown that, right? There exists in the previous class n in z such that, or rather z plus such that this is true. That implies x belongs to, or like k in z plus such that this is true. That implies x belongs to ik. That implies x belongs to I, because the union. So hence I is equal to R. What is R? Both open and closed. So can you see this? It's a closed set. You are taking unions of a closed set and you are getting a open set. So there are little conditions like this. The finite union of closed set are closed, but there is, when this is countable or more than that, it could be open. So this is closed sets. When taking a union, it becomes open. It's closed as well, but it also becomes open. So you cannot say that a countable, this is called countable. I've taught you what countable is. So a countable union of a closed set doesn't mean it cannot be open. Okay? What about Jn? What is J1 for that matter? J1 is minus 1 plus square, sorry. J2 is minus 1 plus 1 over 2 cube 1 minus 1 over 2 cube and so on. Let's plot this. What is this? Something we are adding in minus 1 but very small, less than 1 definitely. So this point lies somewhere over here. This is 1 minus something again, so somewhere over here. This is J1. Okay, you're adding a bit more or bit less actually. So first you're adding minus 1 plus 1 by 4. Which is greater? This is greater, right? So J2, the first point of J2 will be somewhere over here. And what about this? Over here it's 1 minus 1 by 4, 1 minus 1 by 8. Which is greater? Clear? So 1 minus 1 by 8 is again greater. So basically this by red we are doing J2. So what is J2 union J1? It's union only, right? It's J2. And so on, it will keep on increasing unless it hits minus 1 to 1. You can see this cannot go beyond, so it is 2 to the power n plus 1, taking limit, it can only go to 0. Okay, so it is definitely not getting greater than that. So what we can say is J is definitely inside minus 1 to 1. Is it equal? That's the question. So it's a union of, again, countable union of closed sets. Are they equal? Let's say, for just all intent and purposes, you assume that they are equal, right? So this is already true. This is very simple. But if you want to show the equality, you have to show this. Does 1 belong to J? If this is the case, 1 needs to belong to J. But 1 is greater than Jk for any k. So 1 and minus 1 are not there. Basically, J is equal to minus 1 to 1. How do we show this? The only way. Okay, pick an element in J, pick x in J, right? That means x belongs to some Jk. That means x belongs to minus 1 over 2 k plus 1 to 1 minus 1 over 2 k plus 1. This implies x is in minus 1 to 1 for sure. What about the other way? Pick any x in minus 1 to 1. Okay. What you have to show is this thing. You have to find a k where this is true. How do you do that? Since x is in 1 plus 1, what is x plus 1? That implies x plus 1 belong to 0 to 2. It's positive, right? Since it's positive, you can take it down. Take an ln with base 2, you get k plus 1. That's it. You take basically the greatest integer of sk. Does this exist? So x belongs to, so x is basically, this is a polynomial, simple. So where does 1 over 1 plus x go from? So at one place x plus 1 is not 0 but one second. So x plus 1 belongs to 0 to 2. It cannot be 0 anywhere. So it is 1 over, it's not 0. The other thing is what x plus 1 is 2. So it's going from, so if you want to like plot this basically. It's going from 2 to infinity. Can you see this, right? Sorry, 1 by 2. So 1 over x plus 1 is 1 by 2. It is going up to infinity. Okay. What is the value at 1 by 2? Something log with, this is well defined. Right? What is this? Log 2 to minus 1 basically. The value is minus 1. It starts from here and then again minus 1 is over here. I'm just plotting this. And at infinity, it will be infinity, right? At 1 it is going to 0. You're not going to 0. You pick any x basically. You pick any value, you pick any x, you get this point, you get a real number, and we can always get something greater than a real number, an integer. This is always going to be a real number. So that's how you find k. You do similar thing with this side. You want this, let's say r, right? And what you do is again 1 minus x. So what will this imply? Minus x belongs to 1 minus 1. So basically minus 1 to 1. You add 1. So 1 minus x also belongs to . 1 0 to 2. Right? So 1 minus x also belongs to 0 to 2. It's positive. Again you can do this. Again take with log base 2, 1 over 1 minus x. Right? That implies r is again and then, as you know, whenever it is going greater and greater, right? So pick S to be maximum of R and K. There are two numbers, there is a maximum between them, bigger of the two, and then that implies X belongs to J of S, that implies X belongs to J. So you pick any number between minus 1 to 1. If, when we are talking about 1, right? If X was 1, this number would not be defined. Or rather, if X was 1, if I put over here, right? It's 1 by 2, this is minus 2. So if you can think about it, if you want to like put, like if you want to show that minus 1 to 1 belongs to J, this belongs to J, we have already shown. Why does 1 does not belong to J? Okay, because as soon as you put 1, this whole idea, this 1 over infinity is not defined. But as far as over here x is equal to 1 and over here x is equal to minus 1, this term basically, so if you put x is equal to 1, right? Oh, sorry, x is equal to minus 1. What we get from here is, what you want to show is 2k plus 1 bounded by 0, and this cannot be true. Similarly over here, if you take x is equal to 1, 1 over 2r plus 1 bounded by 0. No matter what integer you put, this is not going to happen. That's why 1 and minus 1 does not belong to J. Now, just to complete this, what is the plot of this? Again, 1 minus x is 0 and 2. So again, it starts in the similar manner. I'm plotting just this. It's half. 1 it will go to 0 and something like this. Again, for each point you have a real number, but as soon as you get 1, this condition won't be satisfied. When we are taking it down, we are making it that it's not 0 because it belongs to 0 to 2. Okay, this is important to understand. This is how it's done. So hence, so what was I then? So I was real number and J was minus 1 to 1. So I is closed and J is not. Okay. So question 9. Again, it's a true and false question. A is non-empty, A is a subset such that A and R of A are set minus, or A complement you can say, are both closed. Then A has to be equal to R. They are not saying anything about R of A. Right? So when A is R of A is 5. very simple and very short answer. There are multiple ways to solve this. That if A is closed, that implies R over A is open, and R over A is also closed. Only phi and R are sets which are both open and closed. Hence, R over A is either phi or is either R. But this implies A is equal to R, and this implies A is equal to phi, but A not equal to phi, hence A is equal to R. One second. Okay, this is one way to show, but I have not shown you that basically even in any topological space, any connected topological space, this is the truth, that only R and phi are. So I have not told you this. This needs to be proven, but I have not proved it. So I'll go with another route. This is given in your solution. I'll just explain the solution to you, what it means. So if A is in R and A not equal to phi, right? So there exists a point in A, pick a point X in A, right? So now after this, again we will show by contradiction. Assume R over A is, there are two cases, right? Either R over A is empty or non-empty. So as we are assuming that R over A is non-empty. Then pick a point A, X in Y and Y in R of A. Right? And they're complement of each other. So since they are not equal, without loss in generality, say that X is greater. So now we define this set called S. What is this? Or alpha in X to Y. So there are 2 points X and Y. You can define an interval, nice interval. So what you're doing is they call it A and B. I'll just pick, just change it so you guys can understand it, huh? So what you're doing is, so there are A and B. Somewhere over here. What you're doing is picking out an interval which is an A. S could be empty, could be no. If X is equal to A belongs to A, and this is a subset of A for sure, right? Because A is in A. So S is non-empty as A belongs to S. Okay? And S is bounded for sure, right? Because it's just between A and B, right? So let call this, right? And since B is an upper bound, that implies B is upper bound. Now let epsilon be greater than 0 and consider J is U minus epsilon, U plus epsilon. It's an open interval. Given epsilon, there is some U will be somewhere over here. It could be same as B as well, but somewhere over here inside A and B, right? So now since U is supremum, right, that implies S intersection again, this is the property of epsilon. If you are not clear, you should know this. If there is a set, right, any set, we are not an interval, a set, right, and this is a supremum. So if you take any for positive epsilon, anything less than that, right, there has to be a number between it. If not, that U minus epsilon would have been a supremum. Do you understand? It doesn't have to be an interval. Okay? I hope you are understanding this. If there is some point, it's a supremum, and if I take for some any positive epsilon, U minus epsilon, and if there is no point of S in here, that means this point would have been a supremum. But this is a supremum, that means there is a point of S over here. This is what it means. This is because since S is supremum. So this implies, and this is a subset of this, J, so S intersection J is not phi. What can I say from here? You have at some point you take an interval and it always intersects with S. I hope you are understanding this. there is j, there is some point u, u minus epsilon, u plus epsilon, and s is intersecting with it. There is some set s. Can u be in R of A? You have to understand this, okay? So A to X, this point is in A. Okay? So let's make it more clear. There was A, there is B, okay? There is U somewhere. We don't know where it is U. And S is all the set of points. It could be just A as well. Okay? S could be all the set of points such that this belongs to A. Okay? And there is U minus epsilon, there is U plus epsilon, and I've shown that this S and U, this set intersects. So as soon as they intersect, so there is a point in here, in U minus epsilon, there is a point, let's call it U star, right? Not equal to phi, that implies S intersection, there exists a U star such that U star belongs to S intersection J, and as soon as there is U star, okay, in S intersection J, what does it mean? That this U star belongs to S as well, right? That means A of U star is in A. I hope this is clear.
Yes.
Right? Now, can you belong to, basically this was the question, can you belong to R over?
R minus A means then S, U should be U.
Basically, A ends somewhere over here.
Yeah. So R minus A will be, then U will be part of R minus A.
Can it be? how do you show this? Basically what I'm saying is there are 2 points, there is some point inside this, you don't know what it is, okay, and basically over here there's something that is intersecting it. So this point, basically S is intersecting with u minus epsilon and closed u. There's some point u star, and as soon as that is S, it belongs to u star. A of this closed u star is a subset of A. If you take epsilon smaller and smaller, what should you get?
Get U, right?
So that means this won't be in R of. That implies if u is not in R of A, right? That basically if u is some point between A and B, and if u is in A, right, that implies u belongs to S, and if u belongs to S, that implies u is definitely less than B as B is not in S. Okay, so somewhere over here there is a supremum. Now what you do is you define V as minimum of this u plus epsilon and B. U plus epsilon and B, whatever is minimum. Because u can be very over here and u plus epsilon can go over B. Okay? So let me make 2 cases for it, okay? Very simple cases. This is clear, right? Now let's make 2 cases. Let u is less than equal to B, so let u be equal to B and u be less than B. Okay, so if u is equal to B, right, this is A, this is B, and this is also equal to u. If you take u minus epsilon and then you take u plus epsilon, sorry, u minus epsilon and u plus epsilon. Okay, and what we have shown is that this J intersects with S, so there is some point u star over here. And if we put epsilon smaller and smaller, this will imply B is equal to S, but B belongs to R of A, that implies B is not in S. And another case is U, B greater than U. Okay, in that case, define V as minimum of U plus epsilon and B. What is that? Right? This case. So U could be very near this, U plus epsilon can go above this. So this is the case. So in this, basically there are two cases, that this is A, this is B, right? If U plus epsilon, basically U is over here and U plus epsilon is over here, and this is V and this is A, this is B, and if U plus epsilon is inside this, then this is V. Okay? In both cases, V is not in S. So there exists some X in A to V minus A. Since A to U is a subset of A, that implies that X belongs to U to V from U to U plus epsilon. That implies J minus A is not equal to 5 and J is not contained in A. Thus, U is not in A and a contradiction arises. This is a very good question to understand all the supremum and infimum. Okay. Do you have any specific doubts?
No.
No specific doubts. Okay, so I'll just do one more question. Just 1 second. Yeah, okay. So I've told you, right, that let's do this, all the closed set and open set stuff. Okay, so finite union of closed set, what will it be? Will it be closed or open?
of open set is closed, but
I'm talking about finite union.
it is closed. No, finite union means it will be continuous.
No, like just like 5 or 10 or 15 union of closed set. Basically, if you have like I give you some set, A1 is closed, I'm giving A2, A3, and so on. They're closed up to some AK, not going to infinite. It's finite. Will the union be closed?
We can take the complement of that and that will be open.
Okay, so you want to start with this?
If we take a complement of this, then
How do you treat with complement in terms of union?
no, individually I can take.
You can take a complement. So there is a set rule, something like this. And A1C, A2C are all open. So this arises another question. Finite union of finite intersection of open sets. If that is open, then A complement is closed and we are done, right? These are two questions which are related. You prove one of them, you prove both. So let's call this, just calling this same thing as O1, O2. Okay, it's calling it. Okay, and we want to show that this set is open. So what is the procedure of showing some set is open? There is an interval, right? So let X belongs to O. That implies X belongs to all of them, because since it's an intersection, right?
Yes.
Since X belongs to O1, right? That means X plus epsilon and X minus epsilon are contained in O1 for some epsilon. Let's call it epsilon 1. Similarly, X minus epsilon 2 contained in O1 for some epsilon 2, and so on. Take epsilon to be infimum of this. And since this is a finite set, an infimum always exists. It's called a minimum. Take a minimum of this. There are finite numbers, there is a minimum. Right? That implies X minus epsilon, X plus epsilon is contained in same thing is contained in, okay, and these all are contained in O1, O2. That implies X minus epsilon to X plus epsilon is contained in O1 intersection. So for a given X, there existed epsilon such that this is contained in this intersection. That implies this is for every X, right? That implies O is open. That implies A is closed. But do you realize what we have done here? We have taken a infimum. If it was a number going anywhere up to countable, if it was like up to natural number, we cannot always take infimum, right? Right? If it was 1, 2, 3, 4 and so on, or sorry,
that is, if it is not bounded, then we cannot
yeah,
talk
exactly.
about it.
Yeah, bounded from below. So since this is finite, there is no limit, right? If it was 1, 1 by 2, 1 by 4, there is no infimum of things like that, right?
Yes.
So that's why it's important. The finiteness is important. These are two things that you need to react. So finite union of a closed set and finite intersection of an open set. So finite union of a closed set is closed. Remember, the finiteness is important, and this is true. What about arbitrary union of a closed set or even a countable union of a closed set? We already saw that that was open.
Since that complement we have shown it as well.
No. We have already shown before that if it is a countable,
Countable.
then this is not true, right?
Yeah.
In countable, this is not true. We have already shown that. That same thing applies over here as well. The countable intersection of an open set is not open. Sorry. Over here it should be open.
Okay.
Okay? So I think that's it for today. Let's meet in the next class. And
Okay.
we'll see.
Thank you.
Thank you.
Good night.